Yeah, so I'll just start now with the graph theory. Wherever you have a doubt, you can just ask me. I'll try to wrap up the whole content of the graph theory uh, in the given time. So the important portion that you should be knowing from the graph theory, I'll not be going through the basics, what is graph, all those stuffs. I'll just discuss uh, a degree for a directed and undirected graph. Then we'll discuss adjacency matrix and discuss the vertex cover. And these are all important stuff for a paper. And then we'll be discussing the minimum vertex cover in that. We'll discuss vertex coloring also. Here also the minimum number of color that is required to color any graph. Then you have BFS, DFS. I'll just give you an idea about the BFS, DFS tree. How do you make a tree from the graph? And then you have DAG. And then you have topological sorting, longest path. Then we'll discuss the algorithm for the shortest path. Then you have trees. In trees, we'll be discussing the minimum cost spanning tree. Here also we'll be having two algorithms, Kruskal and Prince. One will discuss, any one you should be knowing, okay? Because and the basic idea you should be knowing how does both of the algo work. Here also we'll be discussing about three algo. All the three algo, I'll just give you the basic idea, the digester algorithm, and then we'll be discussing about the Bellman-Ford and the Floyd-Warshall algorithm. Okay, so these are the whole concept that should be knowing if you are attempting this paper on the 1st of September. Okay, is my voice clear? Everything is fine, right? Shall
Yes,
I
sir.
start? Okay, so I'll just start with the degree. So I hope you're aware of the directed and undirected graph, right? So directed graph and undirected graph. So the degree, whenever you define a degree for any vertex, okay, we are just talking about for any vertex, whatever the number of edges that is incident to it, okay. So whenever you have so see, we have for a directed graph, there is nothing called degree. There is like in degree or out degree. So I'll just write it if somebody is writing it out. So for directed graph, you'll be having in degree and out degree. And the summation of both the two is not equals to degree. So this is not, so in degree plus out degree is not equals to the number of degrees. So there is nothing called degree in the directed graph. Okay, out degree. And then for the undirected graph, you directly tell degree as the number of for any vertices, the number of edges that is incident to that vertex size. Okay, that so the total number of edges that are incident to vertex I. So let's for example, if I'm just this is so is this a directed or undirected graph? This is a directed graph, right? B is dependent on A and C is dependent on B. Okay, or you can just think of as there is some flight. You can move it from A place to B place, but there's no flight or you can't move from B to A. Okay, similarly you can move from B to C, but you can't move from C to B. Okay, but if I'm writing like this is an undirected graph, right? You can move it from A to B and B to A. Both are possible. Similarly, from C to A or C to B to C, both are possible. Even it is written like this or like this, both are same. Okay, and any graph, if it is written like this is also a directed graph. Okay, any graph, even though if you have just a one single directed edge, if you are able to see, the whole graph will become a directed graph. Okay, so I hope this is clear. Is it fine? Uh, can you keep on telling so that I'll be able to know that you are listening, or at least you are aware there at. Is
Yes,
it
sir.
fine?
It's clear.
Okay.
Yeah.
Okay. Hmm. Now let's move to the second concept, was the graph coloring. Okay. So graph coloring is what? This is also a simple concept. Here, just the color, number of color required to color every vertex of a graph such that no two adjacent vertex have same color. So any graph, whatever the graph that has been given to you, okay. So the graph coloring is a simple concept. The number of colors that you are requiring, okay, to color every vertices of your graph in such a way. So there is a condition. So you just have to color all the vertices, and the only condition is the adjacent vertex should not be of the same color. Okay, this is graph coloring. In the graph coloring, there is a concept called minimum number of color that is required. Minimum, okay. So whenever you have been asked to color any of the graph and calculate the min, okay, can you please mute yourself, whoever is there? So there's a lot of noise that is coming. Okay. So here in the graph coloring, you can be asked to calculate the minimum number of color, and that is important for, like, if you have seen the previous papers. Every time there's questions that will be asked from the graph color. Okay, so you can be asked to calculate the minimum number of color to color your vertices such that no two vertices minimum number. So graph coloring you can have a more than minimum. Okay, for like for example, I'm just giving you one example. I'm giving you. Let's for example, you have a this is an undirected graph. Okay, can somebody tell me the minimum number of color that is required to color the whole vertices such that will be so only the condition that you have to satisfy is the adjacent vertices should not be of the same color. Okay, let's do it because we don't have much time. So let's start. I'll just, if I'm putting a red color, can I put B with the red color? No, right? Because the adjacent vertex can't be of the same color. Okay, so I'll be putting a blue. I can put blue here. I can put blue here. I can put blue here. Okay. Now the next color that I can put is any color. Let's green. So I can put green here. I can't put green here. I can put green here. Okay. And here also I can put green. The next only left is I can put red again here, right? So none of the adjacent
Sir, I have a
vertices are of the same
question.
color. What? Okay, okay. Sorry. This both can't be of the green color, right? So I'll have to, yeah, red I can put it here. Okay, I can put red there. Red I can put, right? Yeah.
Oh, yeah.
So what's that minimum number of, yeah, minimum number of color that is required was one is
Three.
red and then blue and then green. So three. Okay, if there, so there can be more than three, right? Because I can just take different types of color, right? There can be more than three, but if you have been asked to calculate the minimum number of color, you'll have to do it like this. Okay, randomly you have to start from some vertices and then uh, think of how many minimum number of colors that will be required. There's only one condition that the adjacent vertices should not be of the same color. I hope this is clear. The next concept that we have to discuss is this is clear, right? This is pretty simple. You
Yes.
can just
Yes.
write, yeah. So Okay. The next concept is, I guess, the planar graph you already know. A graph is said to be a planar if it can be drawn in a plane such that no two edges cross each other. It's not important. You just should be knowing the basic concept. Okay. Now the next concept is the minimum vertex cover. So in the minimum vertex cover, so you have a graph, right? And with V as all the vertices and AE with all the edges of the graph. Okay. So V is basically the set of all your vertices. Okay. So minimum vertex cover are the smallest subset of your V of your vertices. So from the vertices, you just have to pick out the smallest subset of V, okay, such that it covers all the edges in graph. Okay, so I'm just telling you. So this is a and this is a B. This C. This is D. Okay. So if I'm just taking, so what has been said. So V will be what? V is what? The collection of all your vertices, CD. So from this bigger set, you just have to pick out a smallest set of the vertices such that whenever you're just taking that vertices, whatever the incident edges are, all the edges should be covered from the smallest subset that you're taking of the vertices. Okay, let's for example, here I'm taking A and B. If I'm taking A, if I'm just taking A, this edge is covered, this edge is also covered, this is also covered, right? Even though if I'm taking B, that is fine. If with B also, if with AB, I can say that all the edges are covered, right? But is it the minimum? Is it the minimum vertex cover? No, right? Because even though with only A, I'm able to cover all the edges, right? So the definition is a pretty simple definition that the smallest subset that you have to pick out from your the whole vertices, the V vertices were the bigger set of all your vertices. You have to take out the smallest subset of the vertices, the combination of vertices, such that it covers all the edges in the graph. Okay, so the given graph, whatever, this is a simple graph where if I'm just taking A vertices, that will cover all my edges because we have three edges, right? AB, AC, and AD. So if I'm just putting one camera here, it is able to capture all the whole, this lane also, this lane also, this lane also, right? So many times this type of graph is used there. So just to have the minimum requirement of the equipment. Okay. So this is one of the uses. Is it clear? Okay, I'll just give you one example. So try to solve the same example. I'll just copy this. I'll just make one more comment. Now, can you tell me the minimum vertex cover for this graph? So it was A, B, C, D, E, G, G was here, E, F, G, H. So the whole V bigger vertices are all your vertices. And then you have to just pick out those vertices such that the smallest combination of the vertices such that you are able to cover all your edges. So if you are taking H, your this vertices is covered, this is covered, this is covered, this is covered, this is covered, right? So the second I can take is B. If I'm taking B here, see that you can just think of as a step as pick the first step can be pick the vertices with the highest degree. So here this is I told you degree. What is degree? So degree is defined for the undirected graph. So this is an undirected graph. So H is having the highest degree, right? You can just think of 5 incident edges are there. So right, 1, 2, 3, 4, 5. So you can start with H. So if you are putting one camera here, you'll be able to cover all this lane, this lane, this lane, this lane, this lane, all the 5 lanes. So just take H first. Then you should not be taking F and D, E, G now. because if you are taking, that's the west. So the next part that you can take is B. If you are taking B, then this is covered, this is also covered, this is covered, this is covered, right? Right? So now what should you take? Okay, yeah, you have to take D, because without D, you can't cover this F. So you'll have to take D. So if you are taking D, this will be covered. This is also covered, right? So now, which edges are left? AC is left and EC is left. If you are taking D, no, D we have already taken. Let's take G,
G, sir.
because G is having, yeah. Go ahead. Yeah. You were asking something?
No, sir. No.
Take C next, right?
Yeah, you can take C. C also you can take. Even G also you can take. Correct?
Apart from C, have more highest degree of right now because it covers B also and E also and simultaneously G also it covers more. It covers more
Which
than
one? No. The step can be. So if you're saying, so the first step can be pick the vertices, pick the vertex with highest degree. Okay, so we started with H. Okay, then we went to B because we was having. And the second step can be go to that vertices which are the highest number of uncovered edges. Okay, uncovered edges. So the next step would be, because some of there can be some vertices with the highest number of edges, highest number of degree, but maybe some of the edges are covered already. So next step would be to go to that vertices, go to that vertex with highest number of uncovered edges. Okay, so we have started with H because H was having 5 uh, degree. Then we went to B because after covering all this 1, 2, 3, 4, 5, B was having 4 uncovered edges. So we went to B, right? Okay. And just to cover all this left part, we took D, so that, because D, if you are taking B, so this was covered, this 4 was covered. Okay. Even though you are taking anything from the right side, DF can't be covered. So you have to take D. There is no option. Okay. And are you getting me or not? Are you able to understand or not?
Can you repeat? I couldn't understand.
Okay. So I'll just repeat. So minimum vertex cover, this, like, the concept is simple. You just have to, so out of whatever the vertices that are there in your graph, you just have to take out the combination of the smallest number of the cardinality. There is a cardinality should be small. You have to take out the subset of your vertices. Okay, some, if you have, let's, for example, for this graph we were having 4 and 4, 8 edges was there, 8 vertices were there. Is you have to take out the smallest number of vertices such that all the edges are covered. Okay, that you have to do here. So what we have done is, if you have been asked to calculate that, if you have been asked to calculate the minimum vertex cover, so the first step is you should start with the vertices that has the highest number of degree, because if you are taking out a vertices with the highest number of degree, you are able to cover the maximum number of edges. Like, we have started with H, and H was able to cover all these 5 edges. Are you getting me or not?
Oh, yes, sir.
Okay. Next step, what we do is go to that vertices which has the highest number of uncovered vertices. The next step should be, and that you should be repeating. Okay. So the next step, this step you should be repeating, keep on repeating. Okay.
Okay.
Yeah. So the next step is you are going to which B, because B is having 4 uncovered edges, because this 5 are covered, right?
Yes.
So we went to B. B is having the number of uncovered edges are 4. So we took B. And after we took B, these all 4 edges are covered, right? So now DF is left, DE is left, and all this AC is left, EC is left, and GC is also left, and EG is also left, right? So now just think of the left side. To cover all the left side, DF, and DE. You can take F also, you can take D also. If you are taking D, DE will be covered and DF also will be covered. If you are just taking F, nothing, only DF will be covered, right? So that's why we
Right.
just took D here. So
Right.
that DF, okay, D is covered and DF is covered. Next move to, let's move to the right side of this graph. From the right side, I took, let's for example, I took G. If I'm taking G, G will be covered, GC will be covered, right? Correct? So
Right.
let's take G. G I took. Then the next part, which are left? C is left and C is left. So you'll have to take C. Okay, if you are taking C, this is also covered, this is also covered, right? So this, if you are dealing with this five can be. Okay, so one more thing, whenever you are just putting this minimum vertex cover, okay, the combination can be different also. But the number, the cardinality should be same. The final answer that you're taking, or like the final answer should be the cardinality for the final answer should be same. The combination can be different, but the cardinality should be same. Okay, like for example, we were able to get 5 vertices in that cardinality. If I'm taking, if somebody, any of you, if you are just able to reduce this to 4, then that will be the minimum vertex cover. Okay, according to me, this should be the minimum vertex cover. Okay,
Understood.
got it right? Everybody got it? We can solve
Yes,
it
sir.
with the other. Yeah, so the next term is the independent set, and there is a relation between the minimum vertex cover and the maximum independent set. So I'll just deal with that. So you have been given a graph with V vertices, all the combination of vertices, and E with all the combination of the edges. Okay, so independent set is here also the subset of vertex. So you have the combination of all the vertices in your V as a set. You can just think of V as a set where all the vertices V1 to Vn, all the vertices are there. You just have to take out the combination of those vertices, okay, such that the condition here is such that no two vertices are connected by edges. See, if I'm taking AB, so our bigger vertices is the set is what? A and B. My one of the independent set can be what? A. The other can be B also. So here the definition, if you'll just read the definition, subset of the vertices such that no vertices are connected by the edges. If I'm just taking A, okay, so are we able to make any edges with only A? No, right? Are you able to understand this? Independent set. Can you hear me?
Yes,
Yes.
sir.
Yeah. Okay. So if AB, this is the graph for you, A and B, that only one edge is there. If I'm just taking one vertices, are you able to make an edge? No, right? Are you getting me?
Yes, sir. Yes.
Huh. Even though if you are taking B only B as a vertex, okay, then also you are not able to make any edges, right? So here in the independent set, there's a concept of maximum independent set. Okay, here you just have to find out the largest set of A. Largest set A, you have to find here largest set A, and A is a subset of A is a subset of V. V was what? The combination of all your vertices of your graph. Okay, such that no two vertices in A, this A, should have a direct edge. So you have to take out the biggest set of the vertices. So you were having the combination of vertices V, and V was V to Vn. All the vertices was there in this bigger set V. So you have to take out all the combination of the vertices, and the cardinality here should be the maximum, such that there they should not be making any direct edge. Okay, so for this example, I just took A and a B. For this example, A, if I'm just taking A can be a maximum independent set because the number I'm taking, this is the maximum number of the vertices. Because if I'm taking AB, that can't be a maximum independent set because AB will make a direct edge. So that's why I can't take AB. I have to take either A or B. So this both can be a maximum independent set for this graph. Okay, are you getting me or not? Is this clear? Yeah, got it. Okay. So the best part about maximum independent set and what the minimum vertex cover is, if you are able to calculate one, we'll be able to calculate the other also. So let's, for example, if A is the largest set that you have found, or you said maximum independent set you have found. Okay, then A complement will be the minimum vertex cover. Okay, so one of the two you should be knowing to calculate, either the vertex minimum vertex cover or the maximum independent set. If you are able to calculate one, will be just do the complement. Will be like complement means if A is a combination of vertex. So for this example, let's for example AB was a graph for us. So minimum independent set you can just think of as A as a vertex with A only. Then A complement will be what? B. So this will be your minimum vertex cover. Okay, and if you are taking B, then A will be your minimum vertex cover. Is it clear?
Yes.
Yes.
Okay, so if you want to do it, okay. Can you tell me the one combination of the maximum independent set? Okay, let's first tell me one independent set itself. Can somebody tell me one independent set? That's it. I'm not asking maximum independent set.
V5, V3.
V5, V3. Yeah, if you would have said V5 only, that is also an independent set, right? Because V5 doesn't make any edge directly, right? If you're taking V5 and what did you say?
V3.
V3.
Yeah.
That is also because V5, V3, there is no direct edge, right? So this can also be independent set. This can also be independent set. Now tell me the combination of the vertices such that the number of cardinality for that set is maximum. Okay, or the maximum independent set you have to tell me. How will you do that? So I start with V3. If I'm taking V3, sorry, V2, I should not be taking this. V1 will get cut down because I can't take V1. If I'm taking V1, then that will make a direct edge. Correct? So I can't take V6 also. Okay, let's take V5 now. If I'm taking V5, I can't take V8 because if I'm taking V8, that will be a direct V1 is already cut down. So now the next part I can take is V7. If I'm taking V7, then V3 will get cut down and V4. So I'll have to take V4. So this can be one of the independent set, or I guess maximum independent set also, I guess. Okay. Are you able to understand this?
Yes.
Okay. Can you move to the next portion? And from here, whatever I said, independent set, graph coloring, and the minimum vertex cover. For sure, there will be some two questions, sir. Okay, from this 3, 4 concept that we have discussed. Okay, let's move to the. If you have a doubt, you can just ask me now, or else we'll move to the next portion.
So can we have one more example of this?
Minimum vertex cover.
Yes, sir. Minimum and maximum independent both.
Okay, let's. Okay. Tell me maximum independent set. You just start from 2. Just take 2. Cut down all the vertices that are directly connected to 2. So if I'm taking 2, I'll cut down 1.
8, 3.
I'll cut
8.
down 3. 8. There is no connection. So there's no connection with
Okay.
8. Yeah, I'll just cut down 1 and 3. Next I can take is 4. If I'm taking 4, I can cut down. 3 is
5.
already cut down. 5 I'll cut down. Next I can take 6. If I'm taking 6, I'll cut down 8.
7.
I'll cut down 5. I can cut down 7 also. What is left? So this can be our maximum independent set, right?
2, 8, 4, 7 would be higher, as in cardinality will be higher.
2, 4.
2, 8, 4, 7.
2, 7, 2, 4, 7, 8.
Yeah.
If I'm taking 2, okay, 1 second. What did I just messed up something. I just took 2 and then cut down 3 and 1. Okay, then I took 4. I cut down. I took 4. 5, I cut down. 3 was already cut down. Then I took 6. If I'm taking 6, 5 is already cut down. 8 is cut down. 7 is cut down. Yeah, if I'm taking 2, no, but okay, yeah, this is the correct answer. 2, 4, 7, 8. Why? Because, so this can be independent set, but this is not the maximum. The maximum can be, because I'm taking 2, 4. I guess, I guess, I'm just taking 2. Then I can't take 3 and 1. Then she took 4. If I'm taking 4, 5 I didn't do, and 3 is already done. So I took 7. If I'm taking 7, 6 is cut down. So I'll be left with 8. So I'll have to take it. Correct. Nice. So yeah. So this is a correct answer. 2, 4, 7, 8 is the correct one. From our perspective, 2, 4, 6, but that was not the maximum. The probability should be maximum. Okay. Is it clear to everyone?
Yes.
Yeah. And what can be the minimum vertex cover? Just take the complement of this. That will be your minimum vertex cover.
Sir, then in the exam, like if as per you did, you went by 2, 4, and then 6 as the first answer which you got. Then if we go by that, is it then advisable to
No, from the see in the exam, if you have been given the options, you can directly check it, right? That
so is
there
it
should
like
not be any direct edge. Okay.
so as per you're saying, then we have to check all the options in this type of questions,
Yeah,
right?
4 options. You can just if you have been given 2, 4, 7, how much time it will take? It will not take 2, 4. There's no combination. You can just directly check it. It will not take much time. If you are able, if you are see, the problem is there is no steps to calculate this. No direct formula or nothing. There is no steps or something like that. It's just that random you'll have to do. Okay.
Okay.
So minimum, or you can do is minimum vertex cover. At least there was something, right, to calculate. Just take out the vertices with the maximum number of edges and then repeat it. Go to the next vertices where the number of maximum number of uncovered edges are there.
Yeah.
Okay. So you can calculate like that, minimum vertex cover, and then do the complement of that. You'll get the maximum independent set. That
Okay.
also you can do.
Yeah.
That can be a, if you think that can be a better option, that also you can do. Okay. Okay. Let's move to the next. If this is your A, then A complement, you can just calculate it. 1, 3,
6.
what is left? 5, 6. This will be your minimum vertex cover. Okay. Let's move to the next part now. The next thing is we have covered degree. Okay, adjacency matrix is left. Okay. So this is simple. So see, you can be given any graph, and then you can this is just another method to represent a graph. Okay. So in the matrix form. So if let's for example you have a graph has a 5 edges. Okay. So I'll start with if you have if your graph is of having a 5 not edges, I'm mistakenly saying vertex to edges. So if you have a 5 vertices, then you'll be having the matrix will be a 5 cross 5 with, let's for example, A, B, C, D, E was your 5 vertices. Okay. So you'll be putting this in the row form and a column form both A, B, C, D, E. Okay, something like that. Okay. And the values are, let's for example, E. Your graph is V and E is the edges for your graph. So here, Aij means ith row and jth column. And the value is 0 if there is no direct edge, and the value is 1 if there is a direct edge. Okay. So let's for example, if I'm just giving you a adjacency matrix, and if you have to make a, give me 1 minute, just 1 minute. Okay, yeah. So what I was saying is, so for adjacency matrix is just the another way to represent your graph. Okay, so whatever the graph had been given to you, you can just put it in the form of a matrix. Let's for example, you have a graph with 5 vertices. So you'll be having, you have to put this all 5 as a row also and a column also. Okay, and if there is a connection, if there is any connection, direct connection, so I and J you can just think of as a, so Aij as the ith row and the jth column. Okay, and if there is a direct connection, the value in that matrix, the value at that place will be putting as a 1, and if there is no direct edges, then you can directly set it as a 0. Okay, let's for example from A to A, so we are not dealing with any self loop, so you can just think of as a there is no connection from A to A. Okay, so it will be 0. So all the diagonal element we can just think of as a 0, and then if there is a connection from A to B, if there is a connection from A to B or A to C, so you'll be putting as a 1. So let's for example, I'm just thinking that A to B there is no connection, and A to C there is a connection 1. So I'll just put it randomly 1. Anything, I'll just put it like that. So see in the first row, if you'll just think of, from A to A there is no direct connection, from A to B also there is no direct connection, from A to C there is a direct connection. Okay, so that graph must be something like that. A to C there is a direct connection. Okay, from A to D there is no direct connection, A to E also no, and B to A there is a direct connection. So you can just think of as a B, so B to A there is a direct connection. Okay, So from the given information, you can just think of this as a graph, okay, with the three about like it will be having more values, and according to that, you can just plot the graph. But till whatever the information that has been given till now, you can just think of as a from A to C there is a direct connection, from B to A there is a direct connection. Okay, so this is how you represent a adjacency matrix. This is very simple concept. The only thing that you should be remembering is if you're not getting any, let's for example, this is a diagonal, okay, and if there is a mirror image, the values are mirror image. If you're just taking diagonal as a mirror and then the values are mirror image of itself, then you can just think of, or generally in the matrix form, you just call it as a symmetric matrix. If you're getting a symmetric matrix, then generally it's a undirected graph, okay. Undirected graph means there will be a connection from A to B and B to A also. If there is connection something like that, A to B and B to A also, then A to B also it was 1, correct, if it's an undirected graph. So that's why I'm calling that if you have been given a matrix and then if I'm asked to say that whether it's a directed or undirected graph, if it is a symmetric matrix, you can directly say that it's an undirected graph, okay. And for the directed graph, it will not be a symmetric matrix. If this is like able to understand that, this is more than enough. Can we move to
Yes,
the
sir.
next part? Is this fine? Is this fine, right?
Yes.
Okay. So the next thing is DAG, okay. So what do you mean by DAG? The directed acyclic graph, okay. What are the some of the features? There should not be any cycle in this graph, okay. This is a directed graph without any cycle, okay. Some of the features you can just think of as doesn't should not be no cycle. And then in the DAG, so if it is a DAG, whether the degree will be defined or in degree or out degree. If it's a directed graph, I told you in the starting, for a directed graph, there's no concept of degree. There's an in degree and out degree, okay. So for the DAG, every DAG, any DAG you can just think of, will be having a vertex, minimum one vertex, with a vertex with in degree equals to 0, okay, and a vertex with out degree 0. Can somebody tell me what do you mean by in degree?
The number
So
of edges pointed to particular vertex.
yeah, so if
Number of
we have been
edges
asked,
connected to that vertex.
not connected. So connected is for degree, okay. So if you have been
Okay.
given a undirected graph with something like that, okay, then A is having a 3, the degree for A is 3, that is for undirected graph. But for a directed graph, degree is not defined. You will be defined, you have a new thing like in degree and out degree. So if you have something like that, A, B, and C with something like that, so A doesn't have any in degree. So there is no vertex, there is no edge that is coming toward A. Okay, so that's why the in degree for A is 0. For B, you can just think of as a 1. Okay, for C, it is 2. Okay, and out degree is what? Going to away from. So for A, it is 2. So the out degree will be 2 for A. And for B, it is 1. And for C, it is 0. Is it clear now? Or should I
Yes, sir.
repeat it? It's clear, right? Okay, let's move to the next. So what I was saying about the DAG. So the DAG for any directed acyclic graph, and this is also important portion. So whatever is important, I'm just telling you all those portions. Okay, I'm not going any detailed explanation of any of the anything. I'm just giving an idea that those are the important and that much you should be knowing. If you are knowing that much, you'll be able to solve because 40% of the paper will be mostly from the graph theory. 35 to 40% of the paper. Okay, so all this concept, every concept will be having one question from you in the exam. You can just after the exam, you can just tell me that this portion doesn't came. So whatever I'm discussing, those are the most important portions. So for any DAG, for any acyclic graph, if you have been asked to check whether it's a racket or not, DAG or not, you'll have to check whether there's a cycle or not. In degree, there must be some vertices with at least one with in degree 0 and at least one with out degree 0. Okay, and you are able, if you are able to do that, or if you have to just check it, you will be able to do the topological sorting. Okay, you'll be able to write some sequence, topological sequence. Okay, or you will be able to find the longest path in that DAG. If you're not able to find, then you can directly say that it's not a DAG. There must be some cycle inside. That's why you are not able to find the topological sorting. Is it clear? Is it clear to everyone?
Sir, can you repeat once?
Okay. What I was saying is, for any DAG, for any graph that has been given to you, and you have been asked to check whether it's a DAG or not, you have to check these four things that I told you. One is there should not be any cycle. If there is any cycle, you can directly say that it is not a DAG, because the name itself says that there should not be any cycle or cyclic graph, directed or cyclic. The second thing is that there must be some vertices, at least one with the in degree 0, and at least one vertices with the out degree 0. Okay, you can see that. Okay, this example itself, is this a DAG or not? This example?
It is
Not a DAG, sir.
Not a DAG. Why?
It's a cyclic
It
one.
is forming a cycle, huh?
it is a
नहीं
DAG.
cycle भी नहीं बन
How?
रहा.
How?
It is a DAG. It
No,
is
no. It's not forming a
DAG.
cycle here. Yeah, no, it's
Yeah,
not.
this
It's
is
not
not
forming a
forming.
cycle.
And you can just, what did I say? No cycle, that is confirmed. Now, next part is in degree 0. So A is having an in degree. So you are able to find one vertices with in degree 0, right? A is having an in degree 0, correct? There is no edge that is pointing out toward A, right? So A is having an in degree 0, right?
Yes.
That is also a feature of a DAG. And then I told you vertices with out degree 0. So you can see that C doesn't have any outward C doesn't have any edge that is pointing out from C. So that's why
Yes.
out degree for C is 0, right? So all the three condition is satisfied for this. So this is a DAG.
Yes.
And then
Yes.
and the next part is, if you are able to calculate the topological sorting. If you are doing the topological sorting, there is some step, 3-4 steps to calculate the topological sorting, or some sequence such that you are able to find the longest path in that DAG or in the graph. Okay, and if you are able to do that, then also you can say that it's a DAG. Okay, so at least three things. If you are able to see that, then you can directly say that the given graph is a DAG or not a DAG. Okay, if that is satisfying, it's a DAG. If it's not a DAG. The next part is topological sorting. I hope this is clear till now. The next part, we are dealing with the topological sorting. Okay, for any plot, we can be asked to write the topological sequence. Maybe it's not like you will be asked, you can be given the option, and from there, you'll be asked to choose that. Okay. Okay. So the next thing is, we were about to discuss the topological sorting. So for topological sorting, there are some 4 steps, okay, that you have to follow. So the first step is, you have to compute the in degree for all the vertices. Okay, you already know that what is in degree. So you have to compute the in degree for all the vertices. Okay, the next step is, now you have to pick the vertex which has in degree equals to 0, because we already know that there must be one vertices with in degree 0 has in degree equals to 0. Okay, and then you are just making an empty topological sorting list, or maybe you can just, it's an empty list. You keep on adding that vertices in this list. The third step would be, remove that vertex. I guess there is somebody. No. and remove that vertex that we have selected that was having the in degree 0. Remove that vertex and all the edges that was incident, all the edges that was incident with that vertex I, or you can just pick that vertex I which has in degree 0 and remove that vertex and all the edges that are incident with vertex I. Okay, and then you have to again update the value, update the in degree for remaining vertex. Okay, is the step clear? So first step is whatever the graph that has been given to you, compute the in degree for each of the vertex. Okay, and then choose that vertex which has the in degree 0. Okay, and whichever the vertex it came, just put it in that empty list. Okay, let's for example A came, so put it A there. Okay, and after that we have to remove that vertex and all the edges that are incident to that, so that is connected either inward or outward, doesn't matter, whichever the edges are there that is connected to that is connected to that vertex with the in degree 0, just remove all those and then you have to update from here, update it and then again pick. So for the drag, that's the best feature, that if you're just removing a vertex with the in degree 0, again whatever the graph has been formed, that is also a drag. Okay, so again there will be one vertices with the in degree 0. Okay, so you can keep on doing that to get your sequence. Is it clear? Is it clear to everyone? Okay, I'll just,
Yes.
are you able to hear me? Okay,
It's clear.
let's,
So can we have a small example of this?
yeah. Yeah. If you have 0, 1, 2, 3, 4. Okay, let's do it. So the first step, what was the first step? What is the first step? Compute the in degree
Check the in degree.
for
Yes.
all the vertices. If you're okay, compute the okay. So what is the in degree for 0? Why did I say in degree is what? The incoming
1.
edges. How many incoming edges?
One.
One, right? It's coming from 2. But in degree for 1,
2.
Two.
here it is 2. Here it is 2 or 3. 2.
Two.
Here it is 0.
0.
Correct?
Zero.
Yeah.
Yes.
Okay. So the first step is done. First step is done. Now next step is
Yes.
pick the vertex with the in degree 0.
Yes.
Which is the vertex with in degree 0? 2, right?
2.
Okay. That we have to pick that vertex and put it in the empty list. So there is an empty list. So just put it there. 2, comma, dash. Okay. And the next step is what? Remove that vertex. We have to remove that vertex 2. And then all the incident edges, all the edges that are connected to that vertex, I have to remove that. Okay. So let's copy it. Okay, so what I have to do? I have to remove this 2, correct? And all the edges that are connected to 2, correct? And then now the next step was what? I have to update the in degree for remaining vertices, right? I have to update the in degree. So I have to update all the in degree. Okay, now what's the in degree?
0.
0. 2,
2.
and 1. Okay, now again we have to repeat it. So in degree has been computed for all. Now pick the vertices with the in degree 0. Which is the vertex with in degree 0? 0, right? Now
0.
put it in the
Yes.
topological list. Whatever the list that we were making, we have to put it there. So 2, after 2, we have to put 0. Correct?
Yes.
Now the next step is what? We have to remove all the edges that are connected to 0. After putting this, we have to remove all the 0. We have to remove that vertex with along with all the vertices, all the edges that are connected to that vertices. Okay. Now let's again copy it. Okay. Let's remove that 2. 0 we have to remove and all the edges that are connected. Okay. So, and our sorting was topological sequence was 2, 0. After removing, what we have to do? Again, we have to update the value of n degree. So, update the value of n degree. What is the in degree? 1? In degree 1. In degree 0. Correct? Again, put it in the, so whichever vertex is with in degree 0, we have to put it in the topological sorting, right?
Yes.
2, 0. Now we have 4. Correct? So, and
Yes.
again we have to, after removing that, we have to remove this and with the edge connected to that 4, right? With the in degree 0, right? Now we are left with again update the value, update it. So if you are updating, here it is 1, here it is 0. So again, we have to take out the vertices with in degree 0, put it in the topological sorting, and then remove that vertex with the edge. Correct? Now we are left with what? 1.
1.
So this is your topological sequence or sorting. Clear?
Yes.
And if you are
Clear.
able to do this, that means that was a DAG. And every step, see, we started from here, right? If you have removed one vertex with the in 0, and after that, whatever the graph that we have got, again that is a DAG, right? Because you can see that one vertex with the in degree 0, right? Now out degree if you calculate, one vertex will be there, whereas out degree will also be 0, and there is no cycle. So whenever you have a DAG, even though if you are removing a vertex with along with all the edges that are connected to the in degree, the vertex that has the in degree 0, again the graph will be a DAG only. It's clear, everyone? I hope
Yes.
it's clear, right?
Yes.
Okay.
Yes.
After topological sorting, there is a concept called longest path in the topological sorting, and then the length that you calculate. So from each vertices, what is the maximum length that you can go? Longest path also you calculate in the topological sorting. So the method will be almost same. Only some method that you have to update. Here, I'll just write it the steps. Mostly you'll be asked to calculate the sorting. Okay, this part you should be knowing. For the longest path, I'll just tell you the procedure. The procedure is, again you have to start with the same thing. So here you have to find the longest path in topological sorting. Here the first step, again the same, compute the in degree. For every vertex. And then initialize LPT, longest path to I equals to 0. So for all the vertices, you just put that longest path from wherever you're starting. The longest path to every other vertices are 0. Okay, for all I that belongs to vertex V. Now the third step should be find the vertex U with, again Y, same thing, in degree equals to 0, and remove it from the DAG. Add that vertex U to topological sorting, the same thing, and give the longest path to that U. The next step would be update the in degree for all the vertices. Same step. Only new thing that we are doing is here vertex that are adjacent to vertex u. And the only thing that you have to do is you have to, after updating the in degree, you have to update the longest path, that length also, LPT, to that I with LPT longest path to I is equals to maximum of LPT to I or 1 plus LPT of U. Do you want me to solve an example or you'll be able to understand this?
So please solve the example.
Longest path. So the same thing. Okay,
Example,
let's deal. Okay, the same example we are solving. Okay, so this is the example that we are dealing with. Okay, the first step is what? You have to compute the in degree. So we have calculated the in degree for all the vertices. Okay, we have to initialize longest path to I. So we have to, another thing, we have to initialize another thing also here. So I'll just take green color. So green color denotes your longest path from the starting point. Okay, and we have started with 0. So green denotes your longest path to any vertices I, and that is 0 for all the cases, 0 0 0 0 0. So brown is representing your in degree value and green is representing your longest path. So from 2 you can just think of as a, from 2 if you have to go anywhere, the longest path is 0 up to now, till now. Now the third step, the first step you have done, in degree calculated. Second step you have done, initialize the value, longest path to all the vertices I as 0. The third step, what did I write? I find the vertex u, find the vertex u with the in degree 0. So again, the 2, we already know that 2 is the vertex with the in degree 0. Okay, and remove it from the DAG, add it to the topological sorting. So here we'll be having two lists. You can just think of as a two list. One is the topological sorting. We started with 2, and 1 you have to write what? You have to write the and the give longest path to that u. So now the longest path is what? 0. Now it's what? 0 is the only, from 2 if you have to go to 2, what is the longest path? The length will be what? 0 only, right? So longest path to that I is 0. Correct? Corresponding to 2, the length is 0. Is it fine or not? Till now it's fine. Step 3 is done. So 1 is done, 2 done, 3 done. Now the fourth is what? You have to update the in degree for all the vertices that are adjacent to vertices u. So what was our vertices u? 2, right? Are you there?
I don't understand how we are getting the longest path.
What? Longest path?
Like, how did we get the 0?
Okay, this 0, because the value we have initialized the value, right? We have kept the value initialized longest path to each
Okay.
vertices as 0, right? In the second step, we initialize the value, right?
Okay.
And after that, we are just taking the vertices with the in degree 0. That means you can't, in degree 0 means what? You can't come to that vertices, right? You have to go away from that vertices only. You can't come to that vertices. If there is some place that you can't go there, right? So the longest path to that place is what? 0 only, because you have to start from where there itself. Because there is no flight. As an example, I'm just telling you, there's no flight that is coming to 2. 2 can just think of as a place. So there is no, you can't go to 2, but you can go from 2 to any other places, right? So there is like the length is 0. If you are starting from 2 and if you have to go to 2, so the longest path will be what? 0 only, right?
0. Got it.
If you just think of as a length, it will be 0, right? So this is what you can just think of as a, just to interpret that. Okay, so now the fourth step, sorry. So the fourth step is, till third step we are done. We have added t to the topological sorting. We have given the longest path to that value also 0. Now the next part is what? Update the in degree for all the vertices. We have to update the value for in degree, right? And uh, update the in degree for all the vertices that are adjacent to the vertices u. Okay, or you can say that why it has been written adjacent to the vertices u, because if you are removing the edges, only vertices that will be impacted is what? The vertices that are connected to that u, right? With the in degree 0. So we have to update the in degree of, you can just think of as a update the value of in degree for all, or you just update the value of the in degree for all those vertices which were connected to that u, or the vertices with the in degree 0. Are you getting me or not? Okay,
Yes, sir.
let's with the example. I'll just tell you. So I'll just copy this again. So the next step was to update the in degree for all the vertices that are adjacent to the u. Okay. So for example, for this case, the next step is what? Update the longest path I. Okay. So for this case, what are the vertices that are adjacent to u? For me, u was what? U is 2, right? Because u was all the vertices with the in degree 0. Correct? So for me, u is 2. 2 is the vertex with the in degree 0. Okay. Now, for me, in the next step, I would be all the vertices that are connected to 2. So the vertices that are connected to 2 are what? 0, 4. Okay. And I have to do what? I have to update the value of LP. I have to update the value of all the vertices which are connected to u and which were connected to u. That means 0 and 4. Till now it is clear or not?
It's
Clear.
clear.
Okay. Okay. One thing we missed. Okay, I'll repeat it again. Maybe that will clarify all your doubt. So the first step was, so we were having one graph. First step was to compute the in degree. So we have computed all the in degree. The first step is done. The second step, we have initialized the longest path to all the vertices. Here I is all the vertices. Okay, so we have initialized the value for all the vertices as a 0. Longest path to each of the vertices as a 0. We have initialized. The third step is find the vertices u which have the in degree 0. So we have find it out that u is what? 2 for our case. The vertex 2 is our u for the first for the third step, and then we have removed it from our graph, and then we have added u to the tabular sorting. So we have added 2 to the tabular sorting, and then we have given the length also. So the longest path to that u is what? 0. Okay, because from 2, if you are starting, if you have to go to 2, we have given the value as a 0. The next step is update the in degree for all the vertices that are adjacent to u. So for me, the adjacent vertices for u is what? 0 and 4. 0 and 4. I have to update the in degree. So what is the updated value of 0? If I'm removing this,
0.
if I'm removing this and removing all the edges that are connected to that vertices with the in degree 0. Now I have to update this. What is the in degree now? 0.
Yeah, for 0
In
it's
degree
for 4 is 1.
4 is 1. Correct. Okay. So now the next step would be what? After updating the in degree for the vertices that are connected to u, I have to update the longest path to the connected vertices. That is what? 0 and 4. Okay. So I have to write it. The longest path to 0 is what? So this is the updation rule. So first you have to update. First you have to get the in degree with the vertices with the in degree 0. Then you have to update the value. Update basically the value whichever vertices that are adjacent to that vertex. Okay, are you getting me or not here? Is it clear or not?
Understood.
Yeah. Go on.
Clear, clear.
Okay. So now the fourth and fifth step is you have to update the value of LPT to 0 and LPT to 4. Okay, this is what you have to update. That is what? Maximum of two things. What was that two thing? maximum of LPT of I or LP1 plus LPT of U. So LPT of U is what? 0. Correct? 0, 1. That is equals to 1. See, why this is 0? Because longest path to 0 was what? 0, right? Longest path to 0 is 0 because we have initialized the value to 0, right? For all the vertices, correct?
Yes. Yes.
Yeah. So now if I have to update the value, see, I just tell you in the layman term. So for 2, if I have to go from 2 to 0 and 2 to 1, because there is a direct connection from 2 to 0, that's why either this statement is what? You just have to do the summation because from 2 to 2 it was 0, you just have to add one edge to go to 2, right? This is what? 0, 1. If the length to go 0 was higher earlier, so then you would have just left it like that. But because here the length is 0, because we have initialized the value with 0 and 0, so one value is 0 and the other value is what? 1 plus 0. So that's why the maximum would be what? From 2, if you have to go to 0, the maximum length would be what? 1. Are you getting me? Is this clear? Is this clear?
Yes, till now it's clear.
Okay. Now, maximum of what? Maximum length to 4. That would be 0, right? Or because earlier the longest path to 4 was 0. Now,
Yes.
0, 1. 1, why? Because this is 1 is from where? 1 plus LPT of 2.
You.
That is 0. 1 plus
Yes.
0. So that is maximum of 1. So now I'll update the value. So I have updated the integrity for 0 and 4. I'll update the value of LPT also. Okay. Clear? LPT of 0 and 4 is updated. Now, next, move to the next part. The next step would be what? I'll just take out. The next step would be to take out that vertices with the integrity 0. So integrity 0 is what? 0, right? Now the next. So integrity was 0 and the updated LPT was what? Updated LPT was 1 for this case, and also for this case it was 1. We have updated the value, right? This is 1, 1. Now the next step is we have to take out I, so we have and add it to the topological sorting. So we have added after 2, we have added 0 because 0 is the value, 0 is that vertices with the integrity 0. So we have taken out 2 and LPT will add it. So for 2 it was 0 because it was 0 earlier. You can see that. Now for 0, 1 is there, right? So 1 will be adding. Okay, and after that we'll remove all the edges that are connected to this integrity vertices. If I'll remove this all the vertices, we are left with this. And what was the incident vertices? For this case, our I will be what? 4 for 0. What was the connected? 0, 3 and 1. 4, 3 and 1. For this, I will be 1, 3 and 4 because from 0, 1, 3 and 4 were connected. Correct? So we'll update the integrity for 1, 3 and 4 because 1, 3, 4 is the only connected vertices, and we will update the longest path also, longest path value, LPT for 1, LPT for 3 and LPT for 4. Clear? So if I'm updating the value, the integrity will be what? For 3, 4 and 1, what will be the integrity? For 4 it will be 0. For 3, what will be the integrity? 1, 1. And for 1, it will be 1 again. Correct? Okay. Now the LPT for 1 is what? LPT for 1 will be what? Maximum of LPT, longest path to 1 or 1 plus longest path to 0. So that will be what? 1 plus 1 is 2. Similarly,
Yes.
for longest path to 3 will be what? Maximum from LPT of 3 to maximum LPT of 3 was 0, comma 1 plus LPT of 0. That is 1. So here also it will be 2. and here also it will be 2. So longest path to 1, 3, 4 is also updated. This is 2, 2, and this is also 2. Is it clear to everyone?
Yes. Yes. Yes.
Yeah. Next thing you can just think of as a next part is what? Again, you have to take out that vertices with the in degree 0. So which is the vertices with in degree 0?
4.
4.
4, correct? 4, you can just write it here. And what is the longest path to 4? 2, right?
2.
2. So after that, what you have to do? You have to remove that vertices and update the in degree for those vertices which are directly connected to 4. So to 4, what is connected? 3, right? So you have to update the value. So remove 4. Okay, remove all this thing. Remove that edge also, and then update what? Update the in degree and longest path to 3, right? So if you are updating the in degree, what is the in degree now? 0, correct? For 3 it is 0, right? In degree now,
Yes.
tell me.
Yes.
Yes, and longest path to 3 is what? Yeah, longest path to 3 is what? So longest path to 3 is either longest path to 3, whatever was there earlier, comma 1 plus longest path to what was connected? 4.
4.
So 1 plus 2, 3, right? So if I'm updating the in degree, so in degree becomes 0 and the longest path to 3 becomes 3, right? Now the next step is what? Again, vertices with the in degree 0. So what is the vertices with in degree 0? 3. Longest path to 3 is 3. Correct? Remove that 3 and the edges also. Now you are left with 4 only. 1 only. So update the value of in degree. So now it is 0. You are left with only 1. Update the value of longest path to 1. So longest path to 1 will be what? Longest path to 1 will be either longest path to 1 itself or 1 plus longest path to 3. What will be the value? 1 plus 3 is 4. So it will be 4. For 0, it will be 4. So this will be the length. If you want to go from 2 to 2, it will be 0. If you want to go from 2 to 0, 1 length. 2 to 4, 2 length. 2 to 3, 3 length. And 2 to 0, what was that? The int was 1, 1. So it will be 4. So this is the topological sorting and this is the longest path to go there. Is it clear to everyone?
Clear.
Clear, right?
Yes.
Okay. Okay. Let's move to the next part now. So we are just half an hour. Okay. So BFS and DFS, right? So that is simple. BFS and DFS. I'll just directly, I'll tell you how to basically draw BFS for any graph. BFS generally breadth first search. What generally you do is, see, that can help you in finding the shortest path from any vertices to the other vertices. If let's for example, this is your plot, and I'll just tell you some of the features also that can help you to eliminate some of the options if it has been given in the form of an option. Okay. So and you have to go in. So whenever in this breadth first search, whenever and you have to do it in alphabetical way. So whenever you are doing this breadth first search, okay. So you have to take the always the alphabetical route. So it will be given in the question because many a times from one vertex you can go to 2, 3 vertices, right? But you have to choose out in the form of alphabetical way. Alphabetical way. Okay. Vertices you can just think of. Okay. Let's for example, I start from A. I'm here. I'll just start from here. So if I'll just start making a tree. I'll just start with A. So from A, how many places I can go? Which all path I can take?
B, D, E.
C, D,
B I can take. Then
E,
B,
D,
D I can take.
E.
And E I can take.
Yes.
Okay. So in breadth first search, you'll start if you have three-way, right? You can start from B also you can keep on going, right? From D also you can keep on going. From E also you can keep on going. So that's why I just made a constraint that you have to take alphabetical vertices. And in the breadth first search, you just have to do the transverse from first B, then D, and then E. So this is why you call it as a breadth first search. Okay. And if it was a DFS, then you would have gone deep. Okay, that's why that is depth first search. This is breadth first search. You have to go till, so you have to transfer from B, then from D, from E. So if from A you were having three options, B, D, E, then you move to B. From B, how many options are there to move? You have from
C,
B,
F.
you have C and F, right? So you can go to C or you can go to F. But from either coming here, you can't go move to C. You have to come back to Delhi. You have to come to Delhi again. And then transfers from D. From Delhi, from where you can go? From Delhi, you can go to G.
Only G.
This is G. What else? No, nothing else, right? So you can just go to G, Germany, right? And then you have E. So from E, can you go anywhere?
D.
D.
From E, you can go. So D has already been taken, so you don't have to do anything, right? Anything else?
No.
No. Then move to C. Then from Chennai, can you go anywhere? No.
F.
From France?
G. D.
From France also you can't go. From France, you can go to Germany, but Germany has already been taken. G has already been taken, right? So you can't go. So now from Germany, you can go anywhere? No, right? So Germany doesn't have any out degree, so you can't go. So this is your BFS 3. Is it clear?
Yes.
Clear? So if I have to make a DFS, how will I make? Let's make it small. Okay. Can you see this, right? The plot you can see, the graph you can see, right? If I have to make a DFS, I'll start with A again. So I can go to B, D, E, any places I can go. Bombay, Delhi, and E for whatever, Egypt I can go, right? But I have to take alphabetical way. So I'll go to Bombay. Okay. And again, I'll not be going to the D. I'll again from Bombay, I'll keep on searching. So that's why this is a depth first search. So I'll keep on going that. So from B, from Bombay, where can I go? In alphabetical way. So I can go to Chennai and France, but I'll have to take Chennai, right? From Chennai, where can I go? From C, what are the options? Egypt and France, but I have to take Egypt, right? So I can go to E. And after E, what are the options? I can go to D. Any other option? No, right? Because E has just the out degree as 1. So I can go to D. From D, I can go to G, Germany. Is there any option from G? There is no option because the out degree is 0. So I can't go anywhere. So then again I have to go back to D. So from D, is there any other option? From D, is there any other option? Despite Germany, except Germany, we can't go anywhere. So again, we'll go back to Egypt. So from Egypt, I was having only one option, D. There is no other option. So I'll go back to C. Is there any other option from Chennai? Yeah, from Chennai, we went to Egypt, but we didn't go to France. So I can go to France now. And from France, is there any other option? From G, I can go to G, but G is already been taken. Shall not be going anywhere. Okay. So from France, again, I'll go back to C. From C, is there any other option? Egypt is done. France is done. I'll go to B. From B, any other option? I already took from B, Chennai already done, France already done. I'll move to A. So America, I can't go anywhere. So I'll already took B done, D done, E done. So this is your DFS. Is this clear or should I explain it again?
Clear, sir.
Clear for everyone?
Yes.
So
You want me to
BFS,
explain it
can
again?
you just explain once BFS, the previous one.
Okay, previous one. Okay, so previous one. And one, so this this works as a stack, right? First in, last out. Okay, and this work in a queue. So first in, first out. See, A, we start with A, correct? After A, I have three options. I can go to Bombay, I can go to Delhi, I can go to Egypt, correct? So I have B, D, and E. I'll start with Bombay because it has been written that you should be following alphabetical order. Okay, if it is not given as order, you can start with Delhi also. But here it has been given alphabetical order. You will be given something. Otherwise, you can have an n number of three. Okay. So
Okay.
from Bombay, you'll have to. What are the other options from Bombay?
C and F.
Okay. So from Bombay, you can go to Chennai. What all? What are the France? Correct? Any other? No. So you can't go and transfer from Chennai. You'll have to come back to Delhi. Okay, because Delhi has came first to from, so that's why this is called as a first in first out. This work as a queue. So if in a queue, if you are standing, if you have came first, you'll get your pizza first, right? If you are in some queue, right? But here in the DFS, if you're coming first, will be going out in the end. So this work as a stack as a concept. This there's some concept stack and this work on a queue. So here, if you're coming first, so Delhi has came first, so Delhi will go up first, go out first. So Bombay is done. C and F. From Delhi, is there any other place that you can go? From Delhi, G you can go, right? So
G.
G is the option. Germany you can go, right? From okay, then let's move again. Come back to the Egypt. From Egypt, is there any other option? You can go to Delhi, but Delhi is already been taken, right? D is done. So from D, E, there is no other option, correct? From E, there is any other option other than Delhi?
Nothing. Got it.
Nothing, right? So this is your BFS 3.
Got it.
Done? Is it done? Can I move to the other part?
Yes.
Yes.
Okay. So some features are there for the BFS. If I'll just write it down, if it came in the options, you can just eliminate the option. The first thing is, in the BFS tree, the original graph that you have made will have all the edges which are in your tree, which are in BFS tree. This simple. The second thing is, whatever the original graph is there, can have edges between two vertices which are on the same level or only one level. The difference should be only one level or one level difference. Okay, there can't be in the original graph, can't have edge between two vertices have more than one level difference. Did you understood this? See, if we have this BFS, you can't have an edge in the original plot. You can have an edge from A to B, A to D, A to E. You can't have B to C. So one level difference is fine, but you can't have A to C in the original graph. So if you have been given something like that, a graph, and then the options can AC be an edge in your original graph? It's not possible, right? So two level difference is not possible. One level is fine. Clear? Is it clear?
Yes.
Okay. Similarly, for DFS also there are some features. I'll just tell you. For DFS, so original graph will have all the, so the first statement is same. We'll have all the edges which are in the DFS tree. The second statement is the original graph can have edges between two vertices which are on the same branch. Which are on the same branch. And this I'm talking about. See this, all these features I'm talking about for undirected graph. Because for the directed graph, you'll be having the concept of forward, backward, and cross edges. Okay, I hope you are aware of that. But that's not important for you now. But it's fine. You should be knowing about the forward, backward edges and the cross edges. For the DFS original graph, the first statement was will have all the edges that are there in the DFS tree. The second statement is the original graph can have the edges between two vertices which are on the same branch. Same branch, you are able to know. If I'm talking about this is the same branch. If you're going from, this is one branch. Okay, another branch. Okay, this you can just think of as a one branch. This is the second branch. Okay, the next statement is the third statement can be original graph can't have edges between two vertices which are not in same branch. So let's move to the some of the three algo that we have to discuss, not in a detail, but just an idea. I guess this statement, this two statement, this one and this one you should be knowing. Okay, because the BFS tree, mostly BFS tree will be given, and then you can be asked which of the following options is correct, and ages will be given. Like I told you for this case, right? You can be said that is ACs and which of the following options are the edges. AC can be one of the options that can't be there. That is not possible because there's a two level difference. Two level difference is not possible in BFS. Okay. Clear? Now move to the three algo that we have to discuss. You should be knowing the basic idea about the three algo. So till now, everything is clear to everyone.
Yes, sir.
Okay. So now we have, and I'll just give you an idea about the three algo. I'll just write digester algorithm, and then you have Bellman-Ford and the Floyd-Warshall algorithm. Okay. The first statement. And where do you use this digester algorithm? This is used to find the shortest path from a fixed vertex to every other vertex in the graph. And there is one common thing is that graph should not be having a negative edge. No negative weight. I hope you already know that negative and positive, not positive, negative weight and negative cycle. You already know, or do I have to tell you? So if let's, for example, if this is a graph and if this is something like that 5, so from A to B, let's for example 5 unit of distance, not distance, maybe if somebody is going from moving from A to B, it's costing 5 unit of some rupee, $5, 5 rupees, something like that. Okay, negative edge means -5. So if maybe let's for example there's some cab auto driver, if he is moving from A place to B place and he's knowing that if I'll just move it from A to B, I can't come to B to A, because maybe there's like it'll cost more, like whatever he's earning, maybe the petrol cost will be more than that. So that's, you can just think of as a, if he's going from A to B, it is costing in a negative way, so he's just losing 5 rupees. So you just think of as if somebody is moving from, that auto driver is moving from A to B, is losing some 5 rupees. So this you can just think of as a negative weight. Is clear? Negative weight. And if you have something like that, cycle. This is, just for example, this is A, B, and C. And if the summation of if the summation of this weight, A is the weight, A, B, C, A plus B plus C. If this is less than 0, then you can just say that this is a negative cycle. That weight, the summation of the weight is coming out to be a negative. So that's why it's a negative cycle. Clear? Difference between negative weight and negative cycle? Can somebody tell yes,
Yes.
no, maybe? Okay. Okay. So Dijkstra algorithm is used to calculate the shortest path from a fixed vertex to every other vertex in the graph. And the graph should not be having a negative edge weight. Okay, no negative edge weight. Then you can use this Dijkstra algorithm. Okay, I'll just tell you the second one is Bellman-Ford. I'll just give you an example of Bellman-Ford and Dijkstra and maybe Floyd-Warshall also. So the next is for the Bellman-Ford. See, for this type of a case where the graph is not having a negative edge, okay, Bellman-Ford also you can use it. Okay, so for Bellman-Ford, here also shortest path from one fixed vertex to any other vertices. Here you can have a negative edge weight also, but no negative cycle. Cycle should not be negative. Negative edge will work. Negative edge weight will work, but no negative cycle. No negative cycle. This should not work. So if it has a negative cycle, it will not work. Bellman-Ford. Bellman-Ford. It's not form. Bellman-Ford algorithm. The third is Floyd-Warshall. See here, this will help you to calculate the shortest path from any vertices to the any other vertices. Okay, and here also the negative edge will not, negative edge will work, negative cycle will not work. So negative edge weight will work, negative cycle not work. Here the benefit is you can calculate the distance from any vertex to the any other vertices. Okay, then why not we are using the Warshall itself, the Floyd-Warshall itself, because the time complexity is better for the Dijkstra algorithm. Okay, let's deal some example. One example for the Dijkstra. Mostly, if you are just knowing this much, where you are using Dijkstra, where you are using Floyd-Warshall, and where you are using Bellman-Ford, that is more than enough for you. Okay, is it clear?
Yes, sir.
Okay, so one example, maybe I'll just give you an example. Okay. So Dijkstra or Bellman-Ford, how does it work? So there's a concept called relaxation. Okay. So see, for example, if you have any vertices, let's for example, this is U and this is V. If the cost for U, so there is some cost. So let's for example, du plus cost to go from C to V is less than dV. Whatever is there for dV, if it is less, so du plus C of d, like the from C, the cost of going from U to V is less than dV, then you can update the value of dV. Then you can update the value of dV as du plus cost of CB. This is what you have to do. Keep on doing this. You can just think of as a pseudocode for the digester algorithm. Even for the Belmont pod also, you do it the same thing. In the Belmont pod, you do it n minus 1 times. Okay, here you just do it and like what are the vertices. So here, because it's not that negative edge is not there. So whatever number of times you do, you'll get the same answer for the digester algorithm. Let's do it for this case. So this is our graph. I have to calculate the shortest path from. I have to start. I'm just starting from here. Okay. Let's think that I have to start from one. Source is one. The destination. 2, 3, 4, 5, 6. I have to calculate the weight. I have to go from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6. Calculate the shortest path. Okay. The minimum weight. Let's start. So in the first thing, I'll just think as that from 1, everything is very far. So infinite, 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 infinite. So every infinite, infinite. So go from 1 to 2 is infinite. Similarly, for all the edges, if vertices, if you go, that is infinite. It is costing infinite. You can just think of as an infinite weight. Okay, what did I say? If you have du plus c times ub less than dv, then you just update the value of dv. Okay, so first in the first iteration it is infinite. Let's start from 1. Okay, if you are starting from 1, it's not this. For this, it's not this. So if you are starting from 1, you can go to 2. And if you start from 1, 0 plus 7 is less than infinite. So what did I say? 0 plus 7 is less than infinite. Then you can update the value of dB as 7. This is what I said, the pseudocode. So I can write to go from 1 to 2. What is the weight? 7 in the first iteration. Can I go from 1 to 3? 1 to 3? 1 to 3. So 0 plus 9 is less than infinite. So I'll update the value for 3 also. That is 9. Can I go from 1 to 4? I can't go. So 1 to 4, there is no direct connection. So this is like an infinite distance now also. 1 to 5, can I go? This is infinite. 1 to 6, 0 plus 14 is less than infinite, right? So that's why 14, first iteration. Is it clear to everyone what we are doing in the digester algorithm? We are just keep on doing the same pseudocode. This pseudocode that we have done, u plus cv less than dv, then update the value of dv. That's it. This you have to keep on doing. Is it clear to everyone? Digester?
Yes.
Yes.
Yeah. So from 1 to 2, what is the minimum weight? The shortest path is this, right? And what is the minimum weight? 7. Correct? So you got it from 1 to 2, you have got it. So, but we have to find it from all the other vertices. So now if we have found that 1 to 2, now you can take the help of 2 to go to any other vertices. Because 1 to 2, you have found the minimum shortest path. So now you can take the help of 1 is already there. You can take the help of 2 also. Now the next part is, can you go from 1 to 3 using 2? Can you go to 1 to 3 using 2? You can go 1 to 2, 2 to 3, but that is already more, right? We have already what, 9 as the weight for 3. 9, here 9 is already there. But from if I'm going via this way, 7 plus 17, that is not less than 9. That is more than 9. So that's why we'll not update the value for 3. We'll just keep 9 itself. Are you getting me? So here 7 is done, but 9 in the second iteration. While taking the help of 2 also, I can go to 3, but that is 17. That is not less than 9. So that's why we'll just keep the value as a 9 as. Now, can I go to 4 with the help of 1 and 2? I can go. 15 plus 7 is what? 22. That is less than infinite. So I'll just update the value of 22. Can I go to 5 using 2? I can't go. So it will be infinite. Can I go to 6? Yeah, 6 I can go without, because with the help of 2 or without, I'll be having 14 itself. So what is the minimum? So in this iteration, the 9 is the minimum. So that's why I can go to 9 with the weight 9 as the minimum. So now if 2 is done, from 1 to 2, the shortest weight is what? 7. 1 to 3, the shortest weight is 9. So now I can take out 3 also. So 1 to 3, I'm done. So now I can take the help of 2 and 3 to go to 4, 5, 6. Let's go to 4. So 2 and 3 is done. Let's go to 4 with the help of 3 or 2. So if I have to go to 4, I can go via this method. If I'm going to this, 22 units it is costing. If I'll go from this method, this way, it will cost 9 plus 11, so 20. So 20 is less than 22. So I'll update the value. So it will be 20. Clear? Is it clear or not?
Yeah, understood.
Yeah. So now, can I go to 5? Can somebody tell me if you have understood? Can you tell me? Can I go to 5 with the help of 2 or 3?
No.
Can I go? We can't.
No, no.
So it will be infinite actually. It will be infinite, right? Can I go to 6 with the help of 2 and 3? Better than 14.
Yes.
3.
That
Yes.
will be
One,
We'll
11.
take
9 plus 2.
Yeah, we can
well
go. Correct. Yeah, 1, 3, 6. 1, 3, 6. Correct. So 9 plus 2 is less than 14. So I'll update the value as 11. Correct. Now 20, infinite 11. 11 is the shortest. Now I'll take out 6. 6 also. 1, 2, 3, 6. So now I can take the help of 2, 3, 4 from 1 to reach out to 5, 4 or 5. Is there any other way to reach out to 4 better than 20 if I'm taking the help of 2, 3, 6 all? I guess no, right? No. I can reach out. No, 4 I can reach out with 20 only, I guess. Because there is only two way. There is only two way. This 22, this is costing 9 plus 11, 20. So this is 20 only. Can I go to 5? Can I go to 5 with the help of 2, 3, 6?
1, 6.
Yeah, I can go. Yeah, 1, 6, 1, 6, 5 I can go. That will cost me 22, 23. Uh, okay, but this is, I guess, 1. Okay, I can
1365.
go. 1365 is much better, right? 9 plus 2
Yeah.
is 11 plus 9 is 20. Yeah, 20. Correct? 165 was also there, but it was costing 14 plus 9, right? 23. But here, if I'm going like this, it will cost me 20 only. Can I reach out to 6? 6 is already done. So out of this, I can take out 4 or 5, anything. So 1, 2, 3, 6, 4. Now, taking the help of all the others, can I go to 5? So I can go to 5, but that will cost me 20 itself. So now it's 5. So you got the idea, right? Shortest path from 1 to 2, what is the length? 1 to 3, what is the length? 1 to 4, 1 to 5, 1 to 6. This is how Dijkstra works. Is it clear to everyone?
Yeah.
yes.
Okay. So let's Bellman-Ford and Floyd-Warshall. Okay, I'll just give you an idea of the Bellman-Ford. You can just skip the Warshall. I can give you an idea, but uh, I'll just tell you that whatever I said, that is more than sufficient for your exam. Because again, if I'll explain it, it will take half an hour for. But Bellman-Ford, I'll just tell you, give you an idea, because we have to. The one most important part is left is spanning tree. That for sure will be communicated. Kruskal or okay, any method you should be knowing. Kruskal, I'll just discuss to calculate the spanning tree with the minimum cost. So I'll just give you an idea about the Bellman-Ford. So for the Bellman-Ford, because Bellman-Ford, it will take. It is a bit hectic. Algo. So you'll have to relax it. Keep on relaxing this n minus 1 time. So let's start with 1, 2. Okay. So what in the Bellman-Ford you can see that we have 7 vertices. Okay. So if you have a 7 vertices, you have to do 6 iterations. 6 times you have to relax all the edges. So Bellman-Ford, you have to relax basically all the edges 6 times. For this case, if you have a vertices n, you have to relax the edges n minus 1 times. Okay. Relaxation, I'll tell you. Relaxation is the same thing. Whatever we have done for the Dijkstra. If we are getting du plus cost of going from u to v less than dv, then update the value of dv. That is what you have to do 6 times for all the edges. Okay. Is it clear? Can you hear me?
Yes, sir.
Okay. Okay, so one more thing, if you want the YouTube link, right? If somebody has missed that, I'll just paste the YouTube link also. So this is the YouTube link. You can just so what you have to do is you have to just for Bellman Ford write all the edges because you have to relax the edges, right? N minus 1 time. So you have 7 vertices here. You have to relax it 6 times, all the edges. Okay, and the relaxation you already know, du plus cost of going from u to v is less than dv. If not, then leave it that. It seems good as the digester algorithm. Clear? Weight also. Without weight, it will not work. So let's for example, the weight for this is -1. This minus 6 is 5. Is 3. This is 1. So all the weights for all the edges are done. Okay. Now what you have to do is you have to relax all the edges, right? If you have to relax all the edges, you have to write all the edges first. Okay, what are the edges? 1, 2, 1, 3, 1, 4, 2, 5, 3, 2, 3, 5, 4, 3, 4, 6, 5, 7, 6, 7. So you have 10 edges. Okay, and you have to relax how many times? In the first, let's start with first iteration. Okay, starting from here. Let's write the value with this. Okay. So I'm starting from here, infinite. So this is same as that one. So I'll just this becomes infinite, 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 infinite. First iteration. Start first iteration. 6, 0 plus 6 less than infinite. So I'll start with 1, 2, 1, 2. So first stage 1, 2, 0 plus 6 less than infinite. Should I update the value? Yes. 6, 1, 3, 0 plus 5, 0 plus 5 is less than infinite. Should I update the value? Yes. 1, 4, 5, 0 plus 5 is less than infinite. Update the value. 2, 5, 2, 5, 2, 5. 6 minus 1 equals to 5 less than infinite. I'll update. 3, 2, 3, 2 minus 2. Sorry, it was 5. 5 minus 2 is 3. 3 is less than 6. I'll update the value. 3. Then next part is 3, 5. 5 plus 1, 6 is less than? No. So 5 it is, fine. 4, 3, 4. 5 minus 2 is what? 3. 5 minus 2 is 3, better than 5. So 3. 4, 6. 5 minus 1 is 4, less than infinite. So 4. 5, 6. Where is 5, 6? 5 plus 3 is 8, less than infinite. So I'll update. 6, 7. 4 plus 3 is less than 8, so 7. So first iteration is done. This we have to keep on doing for 6 times. Is it clear? Is this clear? Yes. No. Are there?
Yes, sir.
Clear, sir, clear.
Okay. Okay. So in the second iteration, if you'll just keep on doing the second iteration again, if we'll start with 1, 2. So this is what 0 plus 6 is 3 is better. So we'll just leave it 1, 3. We'll leave it 1, 4. 0 plus 5, 5. So we'll leave it 2, 5. So 2, 5, 3 minus 1 is 2. Better than 5. So 2. 3, 2. 3, 2. 3 minus 2 is 1. Better than 3. So we'll just keep it there. 3, 5. 3, 5. So 3 is what? 3 plus 1, 4. Is not better than 2. So just leave it. 4, 3. 5 minus 2 is 3. So minus 3 is there. 4, 6. 5 minus 2, that is fine. 5, 7. 5, 7 is 2, 3, 5 is better than 7. So 5. Okay. And then 6, 7. 6, 7, 4, 3. So that is fine. So second iteration done. Third iteration 1, 2, we don't have to do anything. 1, 3, no change. 1, 4, no change. 2, 5. 2, 5. 1 minus 1, 0. Better than 0. Better than 2. So we'll just put it 0. Then 3, 2. 3, 2. 3 is 3 minus 2 is 1. It's fine. We don't have to do anything. 3, 5. 3, 5 is 3 plus 1. So this is better. So no change. 4, 3. 4, 3 is what? 5 minus 2. 3. 3 is done. No change. 4, 6. 5 minus 1, 4. No change. 5, 7. 0 plus 3. So we'll just cut it. 3 is better. 6, 7. 6, 7. 4 plus 3, 7. So no change. Third iteration done. Fourth iteration, no change, no change, no change. 2, 5, is there any change? No change. 3, 2, no change. 3, 5, no change. 4, 3, 5 minus 2, no change. 4, 6, 4, 6, no change. 5, 7, no change. 0 plus 3, okay, 6, 7, no change. So this is your final value. So you can see that I'll just, so from 1 to 2, you'll be needing only 1 as a weight. 1 to 3, 3 you'll be needing. 1 to 4, 4. 1 to 5, 0. Okay. 1 to 7, what is that value? 3. 1 to 6, what is that? 4, right? 4. Clear with everyone? This is done, right?
Yes.
After third iteration, there is no change. So if there is no change, then you can just think of as even though if you, after third iteration there is no change, then after sixth iteration also there will not be any change. Right? So you can just stop it after that iteration where after that when there is no updation in the value, so you can just hold it there, you can just stop it there. I guess this is done. Let's move to the next part, and that is the minimum cost spanning tree. Okay, that is important and you should be knowing that. Okay, see, whatever I have discussed, that is all the things are important except this Bellman Ford algo is important. You should, will not be given to do it. Will be asked regarding where can you use the Bellman Ford, where can you use the digester algorithm. Okay, from the options given. Okay, whether Bellman Ford will work for the negative cycle or not, whether digester will work for the negative cycle or negative age or not. So this type of question will be there. So that's why I'm telling you, you should be knowing the basic idea about the algo. Okay, but from the minimum spanning tree, you can be asked from the graph, just give me a spanning tree that is costing me the minimum. That can be asked. You can use any algo, Kruskal or Pilms, any method. You just have to give me the minimum weight that will be for the spanning tree. That will be, you will be making from your given graph. Okay, let's deal with BFS, DFS done. Spanning tree. Okay. So minimum cost spanning tree. Okay, so this is what you have to make a spanning tree from the given graph. Okay, that is costing minimum weight. Okay, let's do it. Let's use the Kruskal method, Kruskal algorithm to solve one question. So you have to just make a tree that is spanning tree that is costing the minimum weight. Okay, that will be costing the minimum weight. Okay, and I hope you already know about the tree. Tree you already know, right? Tree you already know, right?
Yes.
Yes, sir.
Minimally connected graph. So that graph, all the vertices should be. So if you have been given a graph, if you have to make a spanning tree or a tree, if you have to make all the vertices you have to take, there should be the connection. So you can reach out from one vertices to the other. There should not be any cycle. If you are just adding one edge, it will make a cycle. Okay, that's why tree is defined as a minimally connected graph. Okay, that's connected. All the vertices are connected, but it should not be making any cycle. If you are just taking one extra edges, okay, it will make a cycle. Okay, let's deal with one example. So this is connected. And the weight given is 5, 2, 3, 4, 6, 5, 6, 6, 3, 4, 4, 6. You have to tell me from the given graph, you have to make a tree that will cost you the minimum. That will be costing the minimum weight. Okay. So for the Kruskal algorithm, so this is the very basic algorithm and very simple also. In the Kruskal, what do you do is, so whatever the weight has been given to, so you can see the weight, right? 3, 4, 6, 5, 2. So you just have to put the weights in the ascending order. So can you tell me which is the minimum weight? Out of this all value, what is the minimum? 2, right?
2.
2. Yes.
Okay. So wherever 2 is there, you just have to start with the minimum. So 2 is there. So put, because I told you, if you are making a tree, all the edges should, all the vertices should be there. So tree is defined as minimally connected graph. So all the graph should be connected. So for a connected graph, all the vertices should be there. So you just put it like that: A, B, C, E, G, and F, and D is also there. So you start with B, start with the minimum. So you just put, you can just write all the weights in the ascending order. So the first one is 2. So 2 is connected, you can just write it here, 2. The next, which is the next smallest? E, right? This is the next smallest, right? 3, this or this, AC or EF, anything, right? If you're just writing in the ascending order, 2, 3, 3, so this 3 or this 3. So you just took E, F, if you have made the connection. That was 3. This is 2, this 3. What is the next one? Next one is this 3, right? The next value, 2, this is done, this is done. The next smallest is 4.
4.
4.
Correct? So you can take any of the 2, this or this. If you are taking this, you just put it like this. But now you can't take this 4, because if you will take this 4, it will make a cycle. What did I say? A tree is a
Should not form a
minimally
cycle.
connected graph. This should not form a cycle.
Cycle.
Okay,
Yes.
so you can't take this 4. So this 4 is done. This is also done. These are done. So now what is the next minimum?
So what about
5.
BC?
Which one?
BC, sir. BC.
BC.
VC should be connected. Connect to the.
Oh, okay. Yeah. This is also 4, right? Correct. So this you can make the connection. Yeah. So the next part is, okay, 4 is done. So 4 is done. 5. How many 5s are there? 2, right?
2.
Okay. You can't take this because it will form a cycle. Correct? The next 5, this one.
Okay.
This you can take. So this will make, this you can make. Now the next part is 6, 6, 6. 6, 6, 6. So you, if you are taking BD, it will make a cycle. You can't this. Now the next part is DE. If you are making D, this also make a cycle. So you can't take this. The next DE, DF. This also you can't take. It will make a cycle. So this is your connected graph, because you can see that all the vertices are connected, right? And if you are just making one extra edge, it will form a cycle, right? So this is your uh, minimum cost spanning tree. What is the cost for making this? 3 plus 5, 8 plus 2 is 10. So 5, 3, 8 plus 2 is 10. Okay, okay, this BC we are missing. What was the value of BC? 4, right?
4.
Yeah, so 4 plus 3 is 7 plus 5 12, 14, 18 plus 3 is 21. Okay, so this should be the, if you have been asked to calculate the minimum weight, if you have to plot the minimum cost spanning tree and tell the value of the minimum, that cost or minimum weight, 21 should be the answer. And this can come as a NAT also. Even though you are using Kruskal or PRIMS, from both the cases, you can have a different tree, but you'll having a, the minimum cost will be same. Okay, I hope this is clear to you.
Sir,
Yeah.
if we join D and F, I know all the vertices are covered, but you said one more thing, that if another line will make a cycle. So if we cover D and F,
Okay,
it won't
it will be a
make
cycle, right? If you connect DF, it will be a cycle, right?
Oh, right. Okay, understood.
Yeah.
Now I see it. Sorry.
Is it fine to everyone? So all the important concept has been covered. Okay. So whatever I have discussed, if you just know that much, you will not be missing any questions in the exam. That I can tell you. But you have to solve it like nicely in the exam.
Okay, sir.
Any doubt that you have, you can just ask me, or else we'll just close it. Prim's algorithm, you can just go and see that. One important concept is, whenever you are making a, so see, from both the algo, you'll be getting the minimum cost. The only difference is, whenever you are making the Prim's algorithm, using the Prim's algo, so every time you'll be having a connected graph. And connected means there will be a connection. All the connected graph you'll be getting in this from starting to end. Here, there won't be any connection, but in the end you will be getting a connection, like in the Kruskal if you are making. Okay, because in the Prims, what you start from any vertices. Okay, and then you start keep on going. You keep on checking the minimum edge. So if you are using the prims, you're starting with AB with 5. You'll just see that whichever edge is connected to A and B, the minimum one. So then you'll go to BE, okay, because B is the minimum. Okay, this is how you work from the Prims algorithm. But it's like both are simple, but you can just, in the exam, if you have been asked, you can just use Kruskal. Kruskal is much easier, and without even doing anything, you can just be able to solve it. Okay, the only thing is, whenever you are making using the Kruskal, that there is no connection in the graph. In the end, you will be getting some connected, but for the Prims, you'll be getting the connected graph from the starting. I hope this is clear to everyone. Any other doubt you have, you can just ask me. I'm there. You can just ask me. And I have shared with you the maths. Whoever has mailed me, I just shared with you the. If you just want to see the graph theory का previous term का paper, so this has been discussed by the TAs of our course. The link I already shared with some of you, whoever has mailed me. Okay, if you want those links, you can just mail me. I'll just send you some of the links where the previous term paper has been discussed. Okay, you can just go through for the maths. Okay.
Okay, sir.
Yeah.
Sir, still we don't have any update regarding the hall ticket, sir.
None of you have got.
No, sir.
No, sir.
Okay, then you will be getting it maybe by tomorrow, I guess.
Okay.
Because some of our dashboards are also not working, sir.
Okay, no, I don't think so. There is any worry, but you'll be getting in maybe by tomorrow or day after that. If you don't get, you can just mail me. You have my mail ID, right? You can just mail me.
Sir, can you please share
Will you
your
please
mail?
share your mail
Share
ID
your mail ID
once again?
Yeah, I'll just share it now.